This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 3303 solids. First problems we're going to look at are the axial force diagram problems. We have these two setups. I have a bar with some collars on it where I can apply axial force in the length of the bar. So I have these 10 kilonewtons, 2 times 10 kilonewtons in the other direction, 15 kilonewtons to the right, 20 kilonewtons to the left. So over here I have another example where I have 5 kilonewtons on the end, plus 10 to the left, minus 15 times 2 to the right, 5 kilonewtons back to the left. If you sum all those up, you'll see that both bars are in equilibrium. So the first thing I want to do is cut little sections at the places between the points of application of forces. This is a lot like a shear diagram, except I'm not talking about shear forces, vertical forces, I'm talking about axial forces. So I cut a section right here in this first segment of the beam, of the rod or the shaft, and here's my free body diagram. Note that I want to assume positive for my internal force reaction in. So positive being tension and axial force. So I just assume tension positive and let my sign of my answer tell me whether I've got compression or tension. So I've got 10 kilonewtons to the right. Sum of forces in the X is 0, 10 plus my internal force reaction in. Rearranging, I get N is equal to minus 10, so that's compression. Should show that on an answer like that and erase my negative sign. Let's continue going on this one. In green, I've cut a section here in the middle, extend my free body diagram out a little bit more and catch these other two forces that are applied there. Look at my sum of forces equation. I'm kind of omitting that and I'm just going straight to N is equal to, because I'm going to take it to the other side of the equal sign, if I've got it in the same direction it's going to be negative, and if it's going opposite it's going to be positive. So N is negative 10 for this force. Once again, I've assumed my normal force as positive tension. So I've got negative 10 plus in the opposite direction from N, therefore it's plus 2 times 10 is equal to positive 10 kilonewtons, so that's tension in the middle section. And finally I'm going to cut a section in the blue to the right end. I'm going to take my easier free body diagram, which is to the right of that cut. I could look at this whole section, but it's going to give me the same answer. So here's my free body diagram. I've got my normal force once again assumed in the positive direction, and then my shaft, and then my external force 20 kilonewtons. Summing forces in the X direction, positive to the right, is negative N minus 20, so N is equal to negative 20. That's in compression also. So I can diagram that as section 1 is negative 10, section 2 is positive 10, section 3 is negative 20. I can also look at it like a shear diagram. I start off with negative 10. It's kind of like a support. Then, and that's in compression. I can just look at it and I can see that's going to be under compression. Then I'm going to get some opposing forces, and that causes of 2 times 10 or 20, and because they're in the opposite direction of that, they're going to cause the normal force, axial force diagram, to jump up positive 20, because in this section they create tension. It causes it to jump up to positive 10. Then I keep going. I get 15 times 2 in the opposite direction, which causes it to jump down by 30. So 10 minus 30 is negative 20. So you can see, you can just kind of visually graph these. Let's look at this other example. I start off with the free body diagram here in the middle, in the first segment, with about 5 kilonewtons external to the left. Sum of forces x equals 0. I've assumed my normal force, internal force, axial force, positive, because it looks like tension. So my sum of forces equation is negative 5 plus n, so n is equal to positive 5 kilonewtons. It's in tension. Continuing on, do the same free body diagram here, kind of skipping my sum of forces and just writing it out directly. N is equal to, this produces positive, these add and produce more positive, more tension. So 5 plus 2 times 10 is 25 kilonewtons tension. Once again, look at the right end. Look at the segment to the right of the cut. And here's my sum of force. Here's my external force 5 and my internal force N, assumed in the positive direction to create tension. Sum of forces gives me N is equal to negative 5. So it's in compression. I diagram that the same way, 5, 25, and negative 5. You can also look at it in that shear diagram kind of way. 5 kilonewtons positive, it's tension in this first segment. Then I get 20 more, 2 times 10, causes it to jump up to 25. Then I get 30 in the opposite direction, 2 times 15, causes it to jump down from 25 minus 30 is negative 5, and goes over to the end. So those axial force diagrams are pretty simple. Key is assuming a positive direction for my internal force no matter where my section is cut, and then just doing a sum of forces. A little bit more difficult just because of the sign convention thing is, and I've not graphed this yet, I've got a pipe or something, a rod sticking out from a fixed support at C in both cases, and I have some torsion, torque that's applied to this shaft at two locations, one at the end and one in the middle, of different magnitudes. And so like I said, sign convention is the key thing here. And I want to cut a section in red. Red cut right there, my red drawing. I've got this shaft sticking out like this. I've made my cut right here. So I have to apply my right hand rule by putting my palm, the heel of my palm, heel of my hand on the cut. Thumb points out away. My fingers curl in the direction of positive internal torsion. So they curve over the top. And that's how I've drawn my internal force T1 curling over the top, which is the opposite direction of my 5 kilonewton meters and 3 kilonewton meters that are applied here. I just do a sum of moments about the x-axis, which is this axis passing through the longitudinal direction on the shaft. It's equal to 0. I assume positive is over the top, but this is just for this equation, just happens to be the positive direction for internal torque, internal torsion. So the sum of the moments about the x-axis is 0. It's T1 positive, because it is in the same direction as my positive sign assumption, minus 5 and minus 3, because they are the opposite direction. They're curling over the top at me. T1 is curling over the top away from me. So they're opposite signs. T1 is equal to negative 8. T1 minus 5 minus 3. Rearranging, I get T1 is equal to positive, by my sign assumption for internal torsion, positive 8 kilonewton meters. Let's continue on this example. My blue cut number 2 here is just this end of the segment. Once again, so I'm looking at this piece right here. I've made my cut right there. Same sign convention, put my heel of my hand, thumb out, fingers curl over the top. So I just got T2 opposed by my external force of 3. Write my equation, I get T2 is equal to 3 kilonewton meters. So to graph that, I have positive and negative, and then I have segment CB, positive 8, going over to point B where this torsion drops off. This segment doesn't feel, if you will, the torsion caused at B, so it drops down to this 3 that I calculated down here. And I can also see that just by feeling, become the shaft, be the shaft, and feel the forces that it's under. So that's what that's just positive 8. This is positive 3, and that's my torsion diagram for that problem. Now, this one we reversed the end that's fixed. Still doesn't make any difference. The key is understanding my sign convention. I've got my free body diagram cut here on the red section. Here is my shaft coming out like that, or it's cut at the red cut. So that's that end. So I place the heel of my palm on that end, thumb pointing away, and my fingers curl in the direction of positive torsion, positive internal torsion. And so I've drawn that here. It's curling over the top at me, which is the same direction as these externally applied torques, 10 and 6. Do a sum of moments about the x-axis equation, and I get 10 plus 6, that's my sign assumption, is positive over the top. So I get 10 plus 6 plus T1. Rearranging, I get T1 is equal to negative 16 kilonewton meters. But you can see it has to oppose, my internal force has to oppose my external forces. And so it would be in the opposite direction, which by my sign convention is going to be negative. Okay, continuing on out this last section too, in blue, I've got just this. My sign assumption for positive torque, internal torsion is this direction. Sum of moments equation, I get T2 is equal to negative 10. So I can just kind of look at it and see that also. To graph it, here at T1 in segment BC, I have negative 16, and then it jumps up because it no longer, in this segment, it no longer feels the torque at B, 6 kilonewton meters. So it jumps up 6 to negative 10 right there. Just plotting my answers, I get negative 10 kilonewton meters and negative 16 in this segment.